Math 2414, Partial Fractions, Video 3, Example using long division. After concluding the previous video, I realized that I had not intended to do the long division in that video, but rather save it for this one. However, so that this video can stand on its own, I am going to repeat the long division from the previous video. First, let's take a look at this integral. We're being asked to integrate the rational function x cubed plus x over x minus 1 dx. In order to use partial fractions, which honestly this one doesn't require partial fractions, but it still doesn't satisfy the degree requirement, we need to fix the fact that the numerator does not have the greater degree. So let's go ahead and do the long division one more time, dividing x minus 1 into x cubed plus x. Reminder, all missing powers need to be represented with a zero coefficient. That includes the constant term. So x cubed plus x divided by x minus 1. I'll go through this one without as much hoopla as in the previous video. X goes into x cubed, x squared times. X squared times both of these gives us x cubed minus 1x squared. And then if I subtract, carefully, watch your signs, the x cubes cancel, 0x squared minus 1x squared is positive 1x squared. Bring down the next term and then do it again. X goes into positive 1x squared, positive 1x times. I really don't need the 1 there, but I like to focus on the signs and the coefficients. If we multiply positive 1x times both of these, we will get positive 1x squared minus 1x. And then we can subtract those. Then we can subtract 1x squared minus 1x squared is 0. X minus negative 1x is positive 2x. Bring down the 0 and do it one more time. X goes into positive 2x, positive 2 times. Now we're going to multiply both of the terms in the divisor by positive 2. So positive 2 times x is positive 2x, and positive 2 times negative 1 is negative 2. Next move is to subtract. So if we subtract these, 2x minus 2x cancels. 0 minus negative 2 is positive 2. That's our remainder. So we add on our remainder on top of our divisor. And therefore our function is equivalent to x squared plus x plus 2 over x minus 1. Let's move that over into the integral. Now we have an integrand that we can integrate easily. The polynomial x squared plus x plus 2, that's easy. The integral of x squared is 1/3 x cubed. The integral of x is 1/2 x squared. And the integral of 2 is 2x, all positive. Last one technically would require a u substitution. You would say u equals x minus 1, du equals dx, but anytime du equals dx, you don't actually have to do the substitution, just do the integration rule. And this integration rule would be natural log, plus the natural log of, oops, forgot we have a 2 in front, 2 times the natural log of absolute value of x minus 1 plus c. They're really partial fraction decomposition, and technically this isn't an example of it. You'll see what I mean in the next video. But using partial fractions is not really a way to do an integral. It's a way to rewrite an integral so that we can do that new integral. All right, so I keep saying that this isn't really a partial fraction decomposition. What do I mean by that? Well, recall in the first video, we had two fractions that we added together, and then we also tried to take, well, we also mentioned how to take them back apart. It's the taking apart of an addition or subtraction problem involving fractions from its answer back into its original problem that is called partial fraction decomposition. We really did no such thing here. I guess you could say that if we got a common denominator for all 4 of these terms and put them together, we would get that. So I guess sort of it's a partial fraction decomposition, but really we just did a division problem. In the next video, I'll show you what I mean by actually decomposing a fraction into partial fractions.